Hello and welcome back to my Amiga retro games video series. In the last video I was considering writing some executable compression. So in this video I'm going to be looking at a new SDK and also looking at trying to create a compressed executable using this new SDK. This is Visual Studio Code with an extension for Amiga C or C++ compile, debug and profile. What I did was that I used the command palette Amiga init project function to create a nice new project that actually adds a whole bunch of source code. These quick start details are actually put into the help file as well, which was really very useful. This is actually very easy, very quick and easy to get started working with. So yes, if you like these kind of technical deep dive videos, then please do consider liking or subscribing to this channel or sending me a super thanks. They are all always very much appreciated. I needed to find out where my Kickstart 1.3 ROMs were for the Amiga 500 option. So you have different options. You can actually use an Amiga with a built-in Kickstart, or you can use a specific Amiga version when you choose to debug and execute. Anyway, so this is the source code that I came up with. As you can see, that I've removed an awful lot of source code from the Quick Start demo source code. This was to remove all of the extra bits that I really don't need for this. All I need to do is that I need a run code at function, which basically runs code at a specific passed in address to this function. And this address will be a hard-coded address. And then I have a main function which does the sysbase and custom registers, if you like, initialization. It calls forbid and disable to stop multitasking and stop interrupts, if I remember correctly. It's been a while since I've been doing Amiga dev. There's a very useful function in this SDK, which is to bring up all of the documentation, or at least some documentation. So this was refreshing my memory over and above the memory that was already refreshed when I was looking through the Menace and the Bullfrog example source code. And what this main function does is that it just then, after stopping multitasking and the interrupts, it calls my decompressU function. And decompressU is actually using the LZMPiU algorithm for compression, so it just decompresses that RAM there. And then all we need to do after decompressing to a fixed address, which is then just run that 20,000 in hex start address. So all of this source code is going into my GitHub repository as normal, and I will put links in the description below to this video so you can actually see what I've been working on. This is just an initial test. So the code is very hacky and bodgy. I've just copy and pasted the decompression U functions from my compression tool into here, just to make it quick and easy just to put all of this code into one place. I have a feeling I'm going to alter this code anyway to remove the superfluous error checking and data buffer length checking and everything like that. So this code here actually comes from my Commodore 64 development repository. So the same LZMPiU compression method is also supported in this Commodore 64 compression tool. Funnily enough, this tool also compresses just data files, but it also produces self-decompressing executables. So the original file size, the original Amiga file size, was 47,952 bytes, which is this executable here, and this is in the Amiga virtual hard drive, which is which it can be usable from WinUAE, of course. That's where most of the Amiga stuff goes into, is WinUAE, because it's a very good emulator. Now, when I compressed the executable, just the compressed data size on its own, using the LZMPiU method, there's no executable header on this, so it's just data. It's 22,391 bytes in size. But of course, it needs code, Amiga compatible code, at the start to begin to decompress and then run the data that's there. For a comparison, I used, in one of my previous videos, I used a version of PowerPacker, a relatively old version of PowerPacker, and that reduced the executable down to 27,000 odd bytes in size, which is a good target to get to, right? So the LZMPiU data file on its own is already a lot smaller. So I'm just including with Inkbin into this source code the compressed binary file, and then passing in the start and then the length of that. And then you can see this, the decompression address there is 1FFE0. And then it just calls run at with 20,000 in hex to then start the code. So I can choose AROS, I can choose Amiga 500. I'm just going to choose AROS first of all, which is there we go. It's got a nice little flashy screen effect, and then it decompresses and runs, which is fantastic, right? Relatively quick and easy to actually get to this point. It didn't actually take much coding. It's nice having cross-platform compilable C code, in this case, to do the compression and to import that code straight away. So there we go. It also runs on the Amiga 500, or in the emulated Amiga 500 mode. We can have a look at the size of the executable output, and the output size is 24,184 bytes. So already the LZMPiU self-running decompressing executable is already smaller than the version of PowerPacker that I used. If we have a look at the Amiga executable now in the hex editor, there we go, we can see there's some, okay, there are some names here. There's start, memcopy, etc. Those textual names are symbols, and that's going to be wasting some space. We've also got some symbols right at the end of the Amiga executable. So I'm looking at this and I'm thinking that the Amiga executable that is produced by this SDK can still be optimized to make it a lot smaller. Let's change the C flags so that instead of using OFAST, we use OS, which is optimized for size. We also removed the -G option, which should remove a lot of debugging information. We'll change the linker flags to strip out a whole bunch of stuff as well. So we'll strip out unused rubbish, and we'll strip out other things like symbol names and stuff like that. We don't need those for debugging. So it still builds and it still runs in the Amiga 500 mode, which is great to see, isn't it? It's always a nice surprise when things work like this. And now we can have a look at the size for the compressed executable, and it's a lot smaller, 23,320 bytes. So that saved, what, around about 800 bytes or so by stripping symbols and stuff like that. Yes, the file has got a lot smaller now in the hex editor, so it doesn't have the end offset where we were before. Let's get that screen back. This hex editor has a problem with screen pixel zoom levels for the desktop. It really doesn't like non-standard zoom levels. Anyway, doesn't worry, you just have to minimize and re-maximize the window usually. So looking at this, there are some pieces of memory at the end which look like still they could be a little bit more optimized. So I have a feeling that there's a little bit more that can be done. Let's have a look to see what those symbols could, or those memory areas. Let's have a look at what they could be. Let's save these debugging notes into the test1 directory. Test1 directory is the source code for this initial test. I think a proper compressed executable runner will have to be written in mostly using assembly rather than using C or C++, of course. But we'll see, because we can hand optimize for size a little better, perhaps. But I think the decompression code can be optimized. So we can remove all of this input length and the output length store, and we can just have the source and destination address, right? We don't want the destination length that has been decompressed. We'll also, I think, yeah, we'll now get rid of all of these things from the implementations. There we go. So we're just getting through all of this. We're just removing all of this code. That's the source and destination, but we don't want the source length and we don't want the output buffer length and stuff like that. So this function gets a lot smaller and simpler. Now, of course, we need to change the other functions as well, because they're not going to know about input size or max buffer size. So we need to get rid of that, and we need to get rid of that. And of course, that means that input data end is not going to be known, of course. I think we can remove one level of a function as well, because we don't want to return anything. We'll just have it, we'll just ignore the return, but we don't really want to return anything, I don't think. So I'm just removing that intermediate function, because all it did was check for an error and then return OK or error. So I don't want that functionality. It's not useful for the Amiga self-running executable stuff. So we can get rid of that now. We can just call this function and directly. We don't need that. We don't need the pointer to the data end. We don't need to check for the input data being more than the out or less than the output data end. We don't need all of this error checking. We can get rid of that. Again, we don't need to have all of the input buffer continuity and error checking. We can get rid of all of this. So this is basically going to make the code a bit smaller, because we're removing all of the passing in of superfluous parameters, and we are removing some tests, and we are removing superfluous returns as well. So the more that we remove, the more error checking we can also remove. So we're reducing the number of parameters and everything, which reduces the amount of code. I wonder how much this is going to save at the end of the day. We'll compile it and run it, of course, in a bit, just to see if it still works. It should do, right? This is fairly standard code editing. This compression and decompression code is used quite extensively in my Commodore 64 projects. It's also used quite extensively by a few other people as well who do C64 dev, because it's actually a really nice, simple, relatively simple decompression algorithm that's quite well optimized. It sits in 0 page quite nicely, for example, but the compression ratio is pretty good. The compression tool for the Commodore 64 actually has several different methods of compression, but I think at the end of the day, this LZMPiU method is nearly always, like 99% of the time, the best option in terms of speed and size. We always want to run this code. We are not interested in the data buffer pointer checks and everything else, and the match lengths, boundary checking and stuff like that. We'll just assume that the input data is perfectly fine. We will always consume it. We won't check for any encoding errors or anything like that, and that's because we're just assuming that the input data is perfect and hasn't been corrupted. If this was running on obviously a more complex machine, then memory checking is a good practice, but here we don't really want to do any memory checking or anything. Input data validation, as a general rule, is very good practice, but it's not very good practice when you want to generate very small optimal code. So yeah, we'll just get rid of all of this input data validation, the runtime validation as well. That's nearly it, I think. We have some other returns with -1s, so we're just getting rid of these levels one by one. There we go. And there's another return -1 disappeared now. We don't really care about the returned length, so we'll get rid of that too. That's a calculation that we don't really need to do. Let's just return void. And that reduces even more the code. Right then, so we don't need to check for an invalid match offset. We don't need to check again for an invalid match offset. And the end of data check should be exact. We should not have any other superfluous end of data check. Let me just fall out there. So let's see if that works. And it looks like it's working. Yep, there we go. It's still working. Now let's have a look at the output executable size. Now that all of the superfluous code has been stripped out, 23096 bytes, 23,096 bytes. So there we go. That saved 200 odd bytes, which is always nice to see. It's nice when code like this works. Especially it would be quite difficult to debug since I've removed all of the debug symbols. I mean, I could add them back again, of course. Just updating my debugging notes here for everyone's benefit. Let's have a look at the file now in the hex editor, and we have this rather strange block of codey data type stuff in the middle here. I think that's the transition between the decompression code and the actual compressed data. Looks like it. So if we look for where the compressed data actually sits in the compressed executable now, so we'll copy the block hex values from just the compressed data file, and then we'll have a look for those hex values. Look for the hex values. There we go, in the output data. And there we go. There is the start of the compressed data. So at the end of the executable, there seems to be a little bit of data. We could look at the source. We could look at the executable disassembly, of course. We could actually see what's in there. This disassembly file is actually produced by the make file, which is the demo make file in this Amiga SDK, and it contains the offsets and things. I think we might just be seeing some data space or something like that. So these offsets inside the disassembly, the offsets from the start of the section, not from the start of the file. So the start of the section is going to be around about here. So you see, that there's some data there which is not in the disassembly. So I'm thinking that we can get rid of the run code at function here and just include a jump to the start address with an inline assembly. So let's comment out the code here, and then we'll just put some inline assembly into the main function itself. I think comment out the run code at function in the main function, and then in the main code, and then just put a jump. We are not returning back to the desktop or anything. Let's compile and run this. Should be a lot smaller, well, a little bit smaller now, because we removed one function, and I don't think that function was being inlined, you see. Okay. A little bit smaller again, I think. Let's just double check the size, 23080 bytes now. So that's a new personal best, if you like, for this compressed executable size. Just update the debugging notes for what was done, which is remove the run code at and return, and no return, rather, just use a jump. What else can be removed? I removed some defines, but the defines don't actually alter the size of the code at all. So I think for now I'll just leave this video here. I've done pretty much what I wanted to accomplish for the first test of a self-running compressed executable. And now the next one is to probably go into the test 2, which is going to be to parse different hunks and to allocate hunks in chip and or fast for data and code and data, or data and code, depending, and then to put them in the right place, and then to make sure that those allocated blocks get freed on process exit, and to actually probably make sure it returns back to the workbench properly. I think that's what's going to be in the next video. So thank you very much for watching. If you like these kind of retro videos, then please do consider liking or subscribing to this channel, and I hope to catch you around next time. Have a great day, evening or night, wherever you are.